All right, good morning, and here we are again for part 2 of our lecture this morning, and this is going to be lesson 20 for CENG 306, and today we're going to, or for this portion, I shouldn't just say today, for this portion, we're going to look at statically indeterminate torsion. In particular, the learning objective here, we're going to try to use compatibility of deformation, in particular angle of twist, to solve indeterminate torsion problems. So in other words, I want to be able to solve statically torsion problems. Okay, so let us look at statically indeterminate torsion. There will be two cases, two classes. Statically indeterminate torsion. I'll make sure we're recording here, and yes, we are. Okay, good. I'm always paranoid about that after the first day. Statically indeterminate torsion. Statically indeterminate torsion. So there are really two classes that we need to be concerned with. Let's see, say we had a two classes. That we'll need to consider. One, I would say a fixed end compound shaft. Fixed end compound shaft. And then a composite shaft. So both of these will be statically indeterminate. A fixed end compound shaft, or obviously it has fixed ends, that's fairly straightforward. But when we say compound, we mean that it's two different cross sections joined together. Composite would be two different materials. So let us look at the fixed end composite shaft first. I'm going to work through an example of a fixed end composite shaft. So the key for this one, fixed end composite shaft. Fixed end composite shaft. And the key for this is to realize that because both ends of it are fixed, the overall angle of twist is 0. The angle of twist along its entire length is simply 0. In other words, so we have two fixed end reactions. We can twist it somewhere in the middle. It can rotate somewhere toward the middle, but at both ends, from one end to the other, it must be a total of 0. So let us consider this example here. Example 1. So I'm going to have a compound shaft like so. Like this. And then it's going to thin out like this. And I'm going to have points A, B, and C. A will be at the back end, C will be at the front end, and B will be in the middle. A, B, and C. And then this will be, we'll have a certain reaction torque here, TA, and this is going to be clockwise. I'm going to have another reaction torque at C, also clockwise. However, I'm going to have a 100 kip-inch load applied here. So basically, it's fixed here, and I'm applying a large torque to the section at the joint, to the shaft at the joint of the sections, and from that we get we'll get a resistance torque here and here. And then I'll need to give you some dimensions. I'll need to give us some dimensions on my wonderful 3D drawing here. This is going to be 20 inches long, And this is also going to be 20 inches long. Isn't that lovely? Perfectly to scale drawing. Okay, the R for this piece is going to be 2 inches. And the R for this piece is going to be 1 inch. All right, let's see. And we would also need to be told some things about it. We will have, let's see here. I will have some properties which I'll quote earlier that would have to be given to us as well. Now let me just go through the torque diagram. Here, the torque diagram with T in kip inches. So this is going to be positive torque. This is going to be negative torque based upon the right-hand rule. This is going to be TA, and this is going to be TC. However, the distance between them is going to be 100. But we don't actually know the values of these yet because it is indeterminate. The total height difference here is going to be 100. So there's going to be a 100 kip inch difference between TC and TA, but we don't actually know the value of each of these. Okay, so we need to use equations of compatibility instead. And so we're going to assume that this is elastic and deformation. We need to use compatibility of deformation. Namely, gamma from C to A, or sorry, not gamma, phi from C to A, the angle of twist from C to A, is equal to the angle of twist phi from C to B plus the angle of twist phi from B to A. But the overall angle of twist must be 0. But then we're also going to assume this is elastic. So I'm making an elastic assumption. In other words, LT over JG for BC is equal, sorry, not equal, but plus, plugging these, basically I'm just plugging in the two formulas for the angle of twist for each one of these, or plus LT over JG for AB is going to be equal to 0. And I'm going to call this equation 2. Equation 1 I'll derive in a bit. Doing things a little backwards. This is equation 2, just for fun. If I do a, actually let me go back here and do a few equations based off of this. Sum of torques is equal to 0. So TA minus 100 plus TC equals 0. So therefore, TC equals 100 minus TA. Or TAB equals TA, or sorry, where TAB equals TA and TBC equals TC. This one right here is really going to be our governing equation, though. I'm going to call this one equation 1. This one is equation 1. All right. Then I'm going to set up a, let's see, I'm going to use my compatibility here. Now I know the lengths, and I am told, so I do know the radiuses, and I am also told here, I have to be given this, that the G here for B to C of this material is 11,200 KSI. And the G here for this material is 3,900 KSI. All right, so now it's just really just plug and chug. So substituting in 20 inches times negative TC, which is also equal to negative 100 minus TA. over pi over 2 times 1 inch to the 4th times 3900 KSI plus 20 inches times TA, just TA, not TAC or anything, just TA, over pi over 2 times 2 inches to the 4th power times 11,200 KSI equals 0. But then I could substitute, just as I mentioned previously, I could substitute for this, I could substitute in negative 100 minus TA. And if we do all of this, we will find that TA is equal to TAB, which is equal to 84.78 kip inches. And TC is equal to TBC, is equal to 15.22 kip inches. And once we have those, we could easily solve for any of the stresses we wanted or anything else. But, so in fact, let's do that. So, oh, and let's say I was also given that for each of these regions, I was also given the tau yield. Let's say here the tau max is 25 KSI, or the yield stress is 20. I'm given the yield stress for each of these, the yield shear stress. Tau yield is 25 KSI. Okay, you go away. Here, tau yield is 25 KSI, and here tau yield is 18 KSI. So all of this is given, and what I was actually asked to find was whether tau max is greater than tau yield. In other words, whether we're going to exceed the yield stress on this thing. So we have our two torques, and now I'm going to try to find the solve for stress, the maximum stresses. So once we have the torques, the stresses are fairly straightforward. Solve for stress. And here, tau AB max, the maximum stress along section AB, is going to be equal to the torsion in AB, TAB, times rho max over JE. And the polar moment of inertia is going to be fairly straightforward. And I'm going to write the same kind of formula for BC. BC max is equal to TBC over rho max over JE, the elastic polar moment of inertia. And this is going to be equal to 84.78 kip inches times 2 inches over pi over 2 times 2 inches to the 4th power. And this is equal to 6.75 KSI. And this one here is 15.22 kip inches times 1 inch over pi over 2 times 1 inch to the 4th power, which is equal to 9.69 KSI. And then this is less than, we can check and say this is less than the yield stress for this section of 25 KSI. So we're good. And this one is less than the yield stress of 18 KSI. So we're good. So we satisfy the elastic check, we are going to be just fine. Okay. So let us talk about a composite shaft next. And what we mean by, or what I mean by a composite shaft is not only are we, now in this particular example, you might be saying, hey, if wasn't this a composite shaft here? I mean, we had two different materials. Clearly, if they have different yield stresses and different modulus of ruptures, clearly they're different materials. But when we really talk about a composite shaft, I'm talking that along the same cross section, I have different materials. So the real key here for a composite shaft the key to analyze these will be the following. The key will be that the angle of rotation for material 1 must be exactly equal to the angle of rotation or the angle of twist of material 2. Okay, so let's work through an example of this here and see what this looks like. All right, so let me work through an example of this nonsense. Okay, so exemple dos. Example 2. All right, so I'm going to have a fixed end shaft. And so I'm going to have a fixed end shaft under torque. So seems at first to be very simple, but it's actually, this is where the devil comes in. Devil in the details comes in. So I'm going to have a core that is made of a different material. And things get very ugly now. See, this is, I'm going to have a steel inner core surrounded by a aluminum outer surface, an aluminum outer core. Basically, it's an aluminum section with the middle drilled out and steel inserted into the middle. Aluminum outer core. All right. So let's see. I'm going to need to label some points. I'm going to call this A and B. I need to tell you a load. So this is going to be 120 kip inches. And then I need the length of this thing. And the length of this thing, I'm just going to tell you, is 20 inches. And I will also give you that the outer radius is 2 inches. And the inner radius is 1 inch. Okay? So if I do a sum of torques about 0, or just do a sum of torques, they have to be equal to 0. This leads inevitably to TA equals TB equals 120 kip inches. In other words, our torque diagram is going to look like this. A and B, we just have a constant value torque diagram. Positive 120 kip inches. And this is torque. Okay, and I want to find the maximum shear stress in each element. So I want to find the maximum shear stress in each element. And we can just look up the material properties for steel and aluminum. Find max shear in aluminum and steel elements. Sections, I should say. All right, So we again need a equation of compatibility to solve this. And like I said, the key will be like this. The deformation compatibility equation requires that the angle of twist for each of them be the same. So the angle of twist for steel be equal to the angle of twist for aluminum, or aluminium if you prefer. So I'm going to make another assumption. I'm going to make an elastic assumption, which is usually pretty good. We can always just go and check it. And if we are assumed wrong, we'll end up with a stress that's overly elastic, and in that case we'd have a problem. We'd have to go back and fix it. So LT over JG for steel is going to be equal to LT over JG for aluminum. All right, and so this is then going to be 20 inches times the maximum torque in the, or times the torque in the steel over pi over 2 times 1 inch to the fourth times 11,200 KSI here, just subbing in the material properties for aluminum and steel. So basically, we know that the total torque is the 120 kip-inches, but some of that is going to be carried by the steel core and some of it's going to be carried by the aluminum. And we don't know how much is going to be carried by both of them. So, let's see. Oh, and our equation here, the sum of torque, also gives us another sum of torque. We can say T aluminum plus T steel is equal to 120 kip-inches, if that wasn't clear. And so that's going to be equation 1. The torque carried by the aluminum section plus the torque carried by the steel section must be equal to 0. So this is 20 inches times TAL over pi over 2 times 2 inches. I'll make that a bracket instead of 2 parentheses. Times 2 inches to the fourth minus 1 inch to the fourth, like so. And this times then 3,900 KSI. If we combine this, so this would be equation 2 here. If we combine this, we will, if we simplify this down, we get that, actually, so let me not call this one equation 2, let me call the simplified one equation 2. If we combine and distill all this down, we will get that TAL is equal to 5.22 times T steel. And this is going to be equation 2. Then finally, finding the two torques is fairly easy. Solving. So solve for the torques. I know that TAL, the torque in the aluminum plus the torque in the steel, is equal to 120 kip-inches. And I know that 5, so I can just substitute this in, 5.22 TST plus TST equals 120. And from this, I can easily find that TST, the torque in the steel, is 19.3 kip-inches, and the torque in the aluminum is 100.2 kip-inches. And those are my two torques. After that, it's fairly straightforward to find my stresses, just using the elastic shear stress equation for torque. So T aluminum max is going to be equal to T, the torque in the aluminum, times the radius of the outer radius of the aluminum over the polar moment of inertia over the aluminum section. Same thing for the steel. The max shear stress, or steel max, T steel max, is going to be equal to the T in the steel times the rho of the outer radius of the steel section over the J, the polar moment of inertia of the steel section. Then I just substitute in. This is going to be 100.2 kip inches times 2 inches over pi over 2 times 2 inches to the fourth minus 1 inch to the fourth. Like here. And this is equal to 8.55 KSI, which is less than or equal to our yield stress of 25 KSI. So we're good. The steel is 19.3 kip inches times a radius of 1 inch, or outer radius of 1 inch, times pi over 2 times 1 inch to the fourth. And this gives us 12.3 KSI, which is less than or equal to our yield shear stress of 18 KSI. So again, we are good. And that completes that example. So that's it for examples for today. Finally, I would just like to go through a bit of a comparison between torsion and axial force analogy. Torsion, axial analogy. When you took physics, you probably saw, hopefully you learned, the relationship, or the analogous relationship between linear systems and rotational systems, in the sense that there are comparable variables. So if you think of, say, rotational kinematics, where you have for rotational kinematics, where in the linear system you would have A, your linear acceleration. For the rotational system, you would have alpha, your angular acceleration. Where you have, for example, a V, you would have an omega, etc. So then there's a long series of variables that correspond to linear, and that sort of are analogs between linear and rotational systems. And this kind of analogous system extends even on into mechanics and materials. So we have these two relationships here. Phi equals LT over JG, and delta equals PL over AE. So we can sort of see the analogs of each other. We have a few variables. We have phi, L, T, J, and G. And I'm going to use a little symbol that this is sort of a fuzzy equal sign, meaning these are analogous. They're not obviously equal to in number or anything else, or units even, but well, sometimes units. But these are simply analogous. So phi is the analog of delta. L, well, L is just L. Torque is the analog of the axial force. J is analogous to the area, and G is analogous to E. The modulus of rupture is analogous to the modulus of elasticity. So again, this is the change in angle, this is the change in length. These are the original lengths. This is the load. Both of these are the external loads, the maximum torque applied to a section and the maximum axial load applied to a section. Both of these, J and A, represent a section property, the ability of a section to resist whatever force you're applying. This represents the ability of a section to resist torsion. The area, represents the ability of a cross-section to resist axial load. And then finally, material properties. These are both just measures of material stiffness, one in relation to torsion and one in relation to axial stress. All right, that will do it for today, and that will complete our introduction to indeterminate torque systems. All right, so I'll be back tomorrow if we get more CENG 306. If you have any questions, feel free to email me, and